There are two types of receptors, two families. Two types is better. There are ionotropic and metabotropic. Ionotropic receptors are uh, rapid but short duration. Metabotropics are slow but can have longer effects or action to stay consistent. And ionotropic receptors are also simpler. Metabotropic receptors require second messengers, um, different enzymes, and they can take time. But the steps that are involved in metabotropic receptors can lead to long term changes, even protein synthesis that can have potentially permanent changes. Let's talk about ionotropic receptors. So let's first make sure we know what we're looking at. This is the receptor. The receptor controls an ion channel. That's why it's ionotropic. Okay? So you could think of it as it's a receptor channel complex. What are these? These are ions. This is a neurotransmitter. Okay? When there's no neurotransmitter, the channel is closed. No ions are moving through. Neurotransmitter arrives, channel pops open. And what happens with the ions is whatever the forces of diffusion and the electrostatic pressure want. In this case, we're indicating that these ions, whatever they are coming in. Let's look at a couple of specific examples of ionotropic receptors and what happens. Remember what I said about these channels. They fundamentally work the same as the channels we spoke about earlier. But now where are we? We're in the postsynaptic membrane. The other difference between the voltage gated ion channels in the axon, well, those were controlled by voltage. What controls whether or not these channels are open? What controls whether or not it's in the closed state or the open state? The neurotransmitter. So while axonal uh, channels that we talked about were voltage gated, it's a V. These post synaptic channels are ligand gated. This just means chemical. And specifically, what chemical? Of course, neurotransmitters. So let's go through a few scenarios. Neurotransmitter arrives. The receptor controls a sodium channel. What happens to sodium when the sodium channel opens? Sodium rushes into the cell. What's that going to do to my voltage? Depolarize it. This is our primary excitatory mechanism. Later, we'll talk about what this neurotransmitter is called. Let's look here. Neurotransmitter arrives. The receptor controls a potassium channel. What happens to potassium when a potassium channel opens? It rushes out. What's that going to do to your voltage? Hyperpolarize it. This is inhibition. Let's look at here. Chloride that we've been ignoring is such an important piece of our nervous system. All right, neurotransmitter arrives. That receptor controls the chloride channel. What happens to chloride? Well, we didn't really go over it, but the diffusion gradient is such that there's much more chloride outside than inside. So chloride rushes into the cell. And this again hyperpolarizes. And this is our primary. I used that word main there, but same idea. Inhibitory. Oop. Now, metabotropic receptors are far more involved. They involve G proteins. The alpha subunit has to break off, and then an ion channel is opened. And then there are even more steps involved in other types of metabotropic receptors. If you continue in neuroscience, you'll look at this much deeper. Aha. Now, the vast majority of receptors are postsynaptic, right? Well, not the autoreceptor. Remember, auto means self. So here's our synapse. Most receptors are here, right? We talked about the postsynaptic density. But the autoreceptor is right here. And what it's doing, it's monitoring how much neurotransmitter has already been released. And the autoreceptor is primarily a stop signal. Stop making and releasing transmitter. We have enough. Now, this stop signal can be very stern when there's a lot. But in a situation where there's just a little bit of neurotransmitter, the stop, maybe, if you want, if you're feeling up to it. So the signal is much weaker when the level of stimulation is much weaker. All right? Now, to bring it all together, let's talk a little bit about summation, I guess, in the next video.